Welcome back to this course in blockchain and its applications. So, in the last lecture we have seen Bitcoin NG and we have learned a way to scale up the performance of the consensus algorithms. Today we are actually going to learn a cryptographic technique that can further improve the scalability of the blockchain consensus, or rather in general the consensus algorithm or cryptographic consensus algorithm. So, today we are going to learn about the collective signing or CoSi, which is a scalable signing mechanism, and in the next lecture we are going to learn about that how you can use collective signing or CoSi to improve the scalability further compared to Bitcoin NG that we have seen in the last lecture. So, these are the concepts that we are going to cover today. We are going to learn about this concept of collective signing, and in that context we are going to learn a cryptographic technique which is called as Schnorr multisignature, and we will see that how PBFT can be emulated with the help of collective signing. So, the keywords for today's talk is CoSi or collective signing. So, CoSi is the short form for collective signing, and we are going to learn about this concept of multisignature and in particular the Schnorr multisignature. So, there are different multisignature schemes which are available. So, we are going to discuss about the Schnorr multisignature mechanism. So, this collective signing is a method to protect authorities and their clients from undetected misuse or exploits. Well, so this idea has been taken from a research paper by Saitaiwa et al. So, the title of the paper is Keeping Authorities Honest or Bust with Decentralized Witness Co-signing, that got published in 2016 IEEE Symposium on Security and Privacy. So, that particular paper introduced this idea of this collective signature, and it actually is very much popular in designing a scalable consensus mechanism, or rather a scalable crypto consensus mechanism that can be utilized over blockchains. So, the broad idea of collective signing is something like this. Say, we typically use it in our regular day to day life as well in an institutional authorization. So, for example, whenever I am going to send a letter to somewhere outside via my institute, maybe it is something like that the director of the institute need to sign it. Okay. So, the director of the institute need to endorse it and finally send that letter to some other institute. Well, one example can be that are typically being done, say for example, if the institute wants to nominate me for some award, so the director would like to nominate myself. But the thing is that there are many faculties in the institute. So, this nomination goes through certain procedures. So, typically the department they nominate one faculty from a department. So, then that letter will be signed by the department head, and then that will go to the dean faculty. So, the dean faculty will countersign it, and finally it will go to the director, and finally the director is going to sign it. Well, so that means it basically makes a proof that multiple people have seen this letter and multiple people have authorized this nomination collectively, and it is something like to validate that well, even if one of the person is faulty in this entire chain, the system as a whole cannot be faulty. Well, so that way you will see this process of counter signing, that rather than something getting signed by a single person, you get it signed by multiple persons. Well, such that if some one person become faulty, that does not make the letter faulty, because here we are assuming that the authorities can also be faulty, or rather one of the authority can also be faulty. So, when majority of the authorities is signing on my letter, that basically means that I have been endorsed by the institute as a whole, that this person can be nominated for the award, and that can be an example of a collective signing. So, rather than signing by one person, I am getting it signed by multiple person of the institute who collectively nominating myself, and that way it brings up more validity, more proof, more security, or more trust on the system. Well, so that idea is being borrowed in this collective signing mechanism. So, this collective signing, it proposes a scalable witness co-signing protocol, and remember, so this witness co-signing is also use something like a marriage registry, right. So, in the marriage registry it is not only that the bride and the groom they only sign, but there are witness from the bride side, there are witness from the groom side. So, collectively they are agreeing that well these two persons are going to get married from this day. Well, so the multiple people are endorsing it. Well, so even if one person is faulty, one person is against that, it does not get invalidated. Well, so we believe that when multiple parties are signing together, that becomes a more stronger proof. So, this scalable witness co-signing protocol, it ensuring that every authoritative statement is validated and publicly logged by a diverse group of witnesses before any client accept it. Well, so that means multiple people are endorsing that message or endorsing that reply collectively. Well, so this is basically this collective signing protocol. So, mathematically a statement S that is collectively signed by W witnesses assures the client that S has been seen and not immediately found erroneous by those W observers. Well, so that means rather than relying on a single authority, I am relying on multiple authoritative persons to validate my claim, and that way the client will understand that it is not like a single person has validated it, rather a group of persons from diverse domain they have validated it collectively. So, this is likely to be valid. So, this is the kind of broad architecture for CoSi. So, what typically happens that every record or statement like this record 1, record 2, everything that is getting collectively signed by both authority and all or most witness. So, what is authority? Authority is the single node, say the director of the institute, but while the director of the institute is signing it, at the same time there are multiple other people who are working as witness co-signer. Well, so it is not only the director who is signing, but at the same time the witnesses are signing that well this person has finally signing the document as an authority. Well, so that is the kind of signature, that collective signature that we will do. So, the question comes that how I am going to combine these multiple signatures. So, I need to have a kind of scalable way to combine multiple signatures. Well, so if you just think of that, well, I will repeat the digital signature. So, there are say 5 persons who are validating it, say P1, P2, P3, P4 and P5 are going to validate a message M. So, then I need to first do the digital signature with P1, then what P1 has signed I have to do the digital signature of P2, then I have to do the digital signature of P3 and so on. And then if I want to validate it, I have to validate it in a reverse order. That means, I have to first decrypt it with P5, then decrypt it with P4, then decrypt it with P3. So, that is a long procedure, that is not a scalable procedure. Well, so the question comes that how we can do it in a scalable way, because scalability is something that is our broad goal here. Well, so to do this scalable signing thing, the first idea is that the leader or the authority, it organizes the witnesses in a tree structure. Well, why tree structure we will see later on, because the tree structure is a scalable way of aggregating signatures coming from the children. So, it is something like that a single person do not need to aggregate all the signatures, rather say I have organized it in this way, say the P1, P2, P3, P4, P5, P6 and P7. So, that means when it is signed by P3 and P4, so P3 send its signature, P4 send its signature, P2 combine P3 signature plus P4 signature along with its own signature and send that combined signature to P1. Well, similarly here P5 takes the signature from P6 and P7, combine it with its own signature, that means P5, P6, P7, it got combined and that combined signature is sent to P1. Well, now what P1 has to do, P1 takes one combined signature here, say I am naming it as say P342 and here another signature which I am naming it as P567. So, it gets P342, P567 and it finally gets a combined signature as P342 combined with P567 combined with its own signature, and that is going to be the final signature. Well, so that way within a tree structure we are from leaf to root, we can keep on combining the signature, and later on we will see that this provides a better way to validate the signature in a scalable way. Well, and another interesting stuff of this architecture is that we will again see in later on in details, that the 3 rounds of PBFT, that means you have learned PBFT earlier. PBFT had 3 rounds, this prepare, and commit. So, these 3 rounds of PBFT, they can be realized or they can be simulated with 2 rounds of the CoSi protocol. Okay. How that is being done or how that is being implemented, we will see that in details from a few slides from now. So, to do this CoSi, we rely on a cryptographic technique which is called this Schnorr multisignature. So, let us see that what is mean by Schnorr multisignature and how that is implemented. So, this basic CoSi protocol, it uses Schnorr multisignature that rely on a group G of prime order. So, I am assuming that you have this basic understanding of the group theory. If not, I would suggest you to look back and get a basic understanding of the group theory and what is mean by a group G of prime order. So, on this group G of prime order, we have an important property that the discrete logarithmic problem is believed to be hard. So, what is discrete logarithmic problem? The discrete logarithmic problem is that, say a to the power b equal to y, if a to the power b equal to y, I want to find b. So, I can find out b by doing a discrete logarithmic. So, what is that? That my b will become log y base a. Well, so that you know. Well, so this is basically the discrete logarithmic problem. Now, for a typical integer values of a, b and y, this discrete logarithmic is much more easier. But whenever I have a group G of prime order, with a group G of prime order, if I try to solve this group discrete logarithmic problem, well, so that means if my group is G and say small g is a generator of this group G. So, again I am assuming that you know what is mean by a generator of a group. If not, I would suggest you to again look into that basics to understand that what is mean by the generator of a group. Now, if G is a generator of a group and if I make G to the power a equal to y, then finding out this a which is log y with base G, this is known to be complex and you cannot find it out directly. Well, so such kind of discrete logarithmic problem on a group of prime order is difficult to find out. Well, so that is a kind of difficult problem, just like we have seen that finding out the nonce for a hash. So, the same type of problem this is where finding out this reverse thing is much more difficult. So, if you know G, if you know A, it is easy to find Y. Well, but if you know Y and G, it is difficult to find it. Well, so this is the kind of discrete logarithmic problem based on which this Schnorr multisignature is designed. So, the key generation algorithm for Schnorr multisignature is like this. So, you have a G group G of prime order, say R is the order of the group, and small g be a generator of G, the group G. So, we select a random integer x, well, in the interval 0 to r minus 1, r is the order of the group, x is the private key and G to the power x is the public key. Well, and here comes the discrete logarithmic problem. So, that means if you know the public key, if you know G to the power x, well, even if you know this generator G, but it is difficult to find out the private key. Well, if it is a easy problem, then from the public key anyone can find out what is the private key, but we do not want that. That is the basic idea behind this public key private key pair. Well, in case of asymmetric key cryptography. So, whenever I have this public key and the private key, so x is my private key and G to the power x is my public key, and as I mentioned that from G to the power x it is difficult to find out the value of x because of that discrete logarithmic problem on the group of prime order. So, we take x as the private key and g to the power x as the public key. Now, n signers with individual private keys x1, x2, xn. So, in case of collective signing, I will have assume that I have n signers which are going to collectively sign the message, and their private keys are x1, x2 and xn, and their individual corresponding public keys are g to the power x1, g to the power x2, g to the power xn and so on. Well, later on we are going to see that how we are going to combine these public keys together to find a common public key through which we can validate the sign. Well, as I mentioned earlier, that repeated validation is costly, and we want to design this multi-signature scheme in such a way so that we do not need to do those repeated validation. Well, so once I have these public keys and the private keys for individual signers, so the next step is the signing procedure. So, in the signing procedure, each signer picks up a random secret Vi. Okay. So, this random secret is for signer I, and it generates capital Vi. So, capital Vi is equal to g to the power Vi. Well, so the leader, that means you remember that the leader and every node they are represented in the form of a tree. I have that leader and then I have multiple different witnesses in the form of a tree. So, we will see the exact protocol that how the messages are being propagated. So, the leader collects all such Vi, aggregates them as V equal to product of Vi, okay, and uses a hash function to compute a collective challenge C equal to hash of V append S. S is basically the message that I want to sign. Well, so S is the message that I want to sign. So, you append S with this V. So, V is basically the aggregated value of Vi that have been received from individual signers. They computed this Vi from g to the power Vi, and that way the challenge C is generated. So, this challenge is sent to all the signers. So, when this challenge is sent to all the signers send the response Ri. So, they compute this Ri as Vi minus C of Xi. Okay. Vi minus Cxi. So, the leader computes this aggregate this Ri. So, the leader takes initially this Vi, find out this aggregated V, then it sends this challenge. Once the signers get this challenge, it finds out the response Ri as Vi minus C of Xi. So, that responses are again sent to the leader, and the leader computes the aggregated response as R equal to sum of all this Ri received from individual signers. And my final signature is C comma R. Okay. And how we are going to validate it? So, as I mentioned earlier that validation needs to be scalable. So, to verify it, I first find out the combined public key. What is this combined public key? The combined public key is the product of all the individual public keys. Okay. I had n signers, each signer has this key g to the power xi. So, signer 1 was g to the power x1, signer 2 was g to the power x2, signer 3 g to the power x3 and so on. And that way if I just make a product of them, I will get this final Y, that is my final public key to do the verification. So, to do this verification, I do not do it recursively for each public key. I can get a combined public key and verify it using that. And my signature was CR, right. So, where C was this hash of V append S and R was sum of all the Ri. So, we compute this VV to do the verification, which is g to the power R y to the power C. Well, so once I compute g to the power y to the power C, let RV equal to hash of this VV appended my original message that I have signed, that is S. Well, and if I find out that RV is equal to R, that means the R that I had received, if these two values are same, then I can say that the signature has been verified. Well, now you might now just try to understand that why these two values would be same. Okay. So, whenever I am computing it from this combined public key. So, let us try to see quickly the corresponding proof. So, what we have seen earlier, that the verification key is y equal to product of g to the power xi. Well, so the signature is CR. So, C is H hash of that V append S. Well, and R was sum of all the Ri. Now, I computed Vv as g to the power r y to the power c. Now, if you just replace the value of r was sum of Vi minus c xi and y was this product of g to the power xi. Well, so y to the power c becomes product of g to the power c xi. Well, now if I just expand it, so it becomes g to the power sum of Vi minus Cxi into g to the power sum of Cxi. So, product of g to the power Cxi means g to the power sum of Cxi. Well, so if you just do this product, so the sum of Cxi they gets cancelled out. So, I only have g to the power sum of g to the power g to the power sum of Vi. So, I get g to the power sum of Vi. Well, so g to the power sum of Vi that I can represent that product of g to the power Vi. Well, just from the representation of sum and product for the power notations. So, product of g to the power Vi becomes product of capital Vi because my Vi was equal to g to the power Vi. Well, and product of Vi is equal to V. So, we computed Rv as h of V underscore V appendage. So, V underscore V is actually my V. So, I can replace it with V and finally, I will get R. Well, so that is why Rv will be equal to R. So, this is a kind of simple arithmetic calculation to see that well if I just try to play with this product and sum and this power of the individual components with this discrete logarithmic problem, I can have this interesting public key private key pair where individual can sign with their private key and then I can combine the public keys together to get the final public key that I can use for verification of the final message. Now, if I try to see this entire end-to-end procedure, the entire end-to-end procedure, the CoSi protocol works in this way. So, the leader and other witnesses are organized in the form of a tree. Then that was the in the first phase. In the first phase, what leader does? Leader send that message to all the witnesses. Then all the witnesses compute these individual V values, and these individual V values are aggregated. And to aggregate them, you just need to find out the product. That means V1 that the aggregated V value at 1 would be computed as V3 into V4 into V1. Then at 2 it will be computed as V5 into V6 into V2. Well, so that way the message will come to V0 and the final V value, the signature value will get computed. Then it generates the challenge, the leader generates the challenge C by finding out the hash of V0 and the corresponding message S that is being forwarded to all the nodes, and then they compute this R value, and similar way the R gets aggregated. So, to aggregate the R you need to find out the sum. So, R1 will be the sum of R1 plus R3 at R4, then here it will be R2 plus R5 plus R6. That way the things gets aggregated and forwarded to the leader, and leader finds out the final sum value of R, and you have that C and R as your final signature. So, you can do it in a much more scalable way. Now, interestingly, one CoSi round implement PBFT pre-prepare and prepare phase. So, what was the PBFT's pre-prepare and prepare phase? The pre-prepare phase was to send the message to every other node. So, in one CoSi round the message have been sent to all the nodes and you got one level of response. Well, so if you get that response, that means majority of the witnesses they are agreeing on that. So, you are at a prepare phase. And the second CoSi round that implement the PBFT's commit phase. So, again you can run another CoSi round to get the aggregated value that will tell you that well the nodes are finally agreeing or committing the message. So, you can implement the commit phase in that way. Well, so that way 2 CoSi rounds actually emulate the 3 rounds of PBFT. So, you can use CoSi to emulate the same behavior of PBFT. Well, so in this particular lecture we have discussed about this Schnorr multisignature. There are other multisignature schemes which are also available like this Bonnell-Sacham cryptography, BLS cryptography. BLS cryptography provides another interesting way of generating these multi-signatures from bilinear pairing. That is also an interesting idea, and that indeed much more scalable compared to SNOR multi-signature. You can also look into that, the BLS cryptography. We are not going to discuss it in this lecture, but that is another way of implementing this multi-signature scheme. So, using that multi-signature, you can implement this collective signing idea. So, in conclusion, we have seen today that CoSi can be used to sign a message by multiple authorities collectively. So, your verification is easy. You are doing that verification from the collective public key, and PBFT can be emulated using 2 rounds of CoSi. That means, whenever you are going to implement PBFT, you can use CoSi to implement PBFT. And the advantage here is that you are just using a cryptographic technique to forward your message, and with that cryptographic technique you can get back the message from that tree structure, and getting the message is much more easier. So, in the standard PBFT you will see you had that 2f+1 quorum, well, but here your quorum is not 2f+1, rather with the majority voting, when the majority of the nodes are signing your message, you are done, and you do not need a kind of full connectivity among the nodes. Rather, if you can organize the node in a tree structure, you can get back the message. So, that way from the idea perspective, CoSi is much more easily implementable compared to PBFT, but it emulates the same behavior of PBFT. So, you can achieve Byzantine fault tolerance with the help of collective signing mechanism. In the next lecture, we are going to see that how this idea of collective signing in a scalable way that we can utilize to further improve the scalability of a system, of a consensus algorithm that are typically used in blockchain. So, that consensus algorithm is named as Bitcoin. So, in the next lecture we are going to learn about Bitcoin in details. So, that is all for today's lecture. Thank you all for attending. See you all in the next lecture.